The addition of BH3 to an alkyne takes place in much the same way that it does to the addition of an alkene. Again, BH2 adds to the least or less sterically hindered carbon, and then hydrogen is going to add to the more sterically hindered one. So one of the things is that a carbon-carbon double bond is going to remain after the first addition of a BH3. And so before we've seen another reaction occur, and that can happen here if the carbon-carbon bond is terminal. So if the carbon-carbon bond that's left is terminal, right, then a second hydroboration can take place, right? And so because we can get that second hydroboration, the reaction leads to a mixture of products, and that kind of makes it fairly useless, right? So we want to avoid this mixture of products. When we have mixtures of products, that reduces our yield, and that costs more money, and it takes a lot more time. So we want to find really savvy ways to not have these mixtures of products. So chemists avoid the problem of a mixture of products by using a really bulky dialkyl borane. This is an example of one. It's diisoamyl borane. So that's our bulky. Di just means two. Alkyl just means like those R groups or those big carbon groups, which you can see there, right? So those are big hydrocarbon groups. And so borane, of course, just means there's a boron there, okay? Now, diisoamyl reacts with the alkyne in the usual way, the way that we've learned what we would expect, with the big R group, Br2 group, right? So a lot of times, which you can see like right here, this is super big, it's really bulky. So it's gonna add to the less sterically hindered carbon, right? So it adds to the less sterically hindered carbon, okay? And just like we saw previously. Now, with the bulky R2B group attached to the carbon-carbon bond, a second addition of the diisoamyl borane doesn't occur, so hydroboration stops at the alkene stage. So hydroboration stops at the alkene, okay, because it's too bulky to continue to react. And so then we can do another reaction where we have a oxidation in a basic solution of hydrogen peroxide, which is H2O2, and that's going to convert that R2B substituent on the alkene into an OH group. And you can see the OH group right here. Now I want you to notice this is an OH group next to a double bond. So this product is an enol, and it's going to undergo tautomerization to transform into that keto form, because that's the more stable form that we see. Now, in this case, what we see here is an aldehyde. And so we can kind of summarize this as saying, look, this hydroboration oxidation is a really useful way to convert a terminal alkyne into an aldehyde. Okay. This reaction can also be used to convert an internal alkyne into a ketone, but again, we get a mixture of products unless that alkyne is symmetric. And so again, mixture of products is not what we want. I want you to notice that we here have synthesized hexanal. This is also an oxidation product of linoleic acid, and it's thought to be partially responsible for the distinct flavor of cooked meats. So if you are a meat lover and you love that flavor of a good steak cooking, that's really what you're smelling there, or is one of the compounds that you smell there. Now, diisoamylborane isn't the only bulky dialkyl borane that's used to carry out these kinds of conversions. Two other really useful ones are shown here. One is a dicyclohexylborane, and then one is 9-borobicyclo 3,3,1 nonane, which is abbreviated as 9-BBN. This 3,3,1 here indicates kind of where we see the that ring taking place, right? You don't have to worry about that nomenclature. That would be covered in a more upper level course. But these are two that you'll see pretty frequently, most often by this particular abbreviation here. Okay. Now, overall, this chapter has introduced a lot of different electrophilic addition reactions, and what kind of groups these reactions together is that they all involve a cyclic transition state. Now, having spent the bulk of the chapter focused on the mechanisms for those reactions, what we do at this point in the chapter is turn and think about how are these reactions used in synthesis. Particularly, it's really important to understand that you need to be able to apply transforms to these reactions to determine the possible precursors, and that'll help you carry out retrosynthetic analyses more efficiently. In kind of earlier in section 13.2, it described how an alkene can react with a carbene produced in situ from diazomethane to form a cyclopropane ring, which conserves the stereochemistry across the carbon-carbon double bond, right? And so when our target contains a cyclopropane ring, right here, that contains a CH2 group, okay, we can then kind of think about applying a transform like we see here based on what we saw in section 13.2. Okay, I want you to notice that we're going to put these groups on the same side, and so these are shown as being on the same side because they both have the same solid wedges. Understand, if they both had the dashed wedges, they would still be shown on the same side. They've just flipped the molecule around. But because these are the same solid wedges here, it means they're on the same side. And so these groups are on the same side of the double bond, okay? And so I want you to notice the stereochemistry, that if they're on the same side here, the stereochemistry is conserved and it's on the same side here, okay? And so we would want to start with something that was cis to also end up with those groups on the same side, okay? Now, in section 13.3, we learned that peroxy acids like MCPBA will epoxidize an alkene, conserving the stereochemistry in process. So when an epoxide is called for in the synthesis, and so remember this is the epoxide, right? We can then undo the epoxide or apply this transform. And I want you to notice again, look at the stereochemistry. Here we have one is on the dashed wedge here and one's filled in. That's that trans stereochemistry. One's above the ring and one's below the ring. And so we need to have the groups on the opposite side of the double bond here, which is shown as kind of trans as well. Okay, so those groups are on the opposite sides. Now, I want you to notice something. When it's a zigzag like this, that indicates the groups are on the opposite side. If it forms more of a U shape, that means those groups are cis, right? So that's something to pick up with how these are shown. And again, this would be applying the MCPBA Ba to the transform. Okay, and so we're going through our different sections here. So we did 13.2, 13.3. In section 13.4, we studied reactions that produce brominium and chlorinium ion intermediates. And I want you to remember, in the absence of a nucleophilic solvent, Br2 or Cl2 will add anti across a carbon-carbon bond of an alkene, right? So let me just write that. In the absence of a nucleophilic solvent, Br2 or Cl2 will add anti across the carbon-carbon double bond of an alkene. Okay, so in water, which is a nucleophilic solvent, okay, a halohydrin is formed. Okay, so if you are in water, which is a nucleophilic solvent, a halohydrin is formed. Now, that halohydrin, right, is going to have the OH and the Br, right? So those two groups are added there. I want you to notice that, again, this is an anti-addition of the OH and the halogen across the carbon-carbon double bond, okay? And I also, don't forget, molecular halogens will also add across a carbon-carbon triple bond to produce a tetrahalide. So this can happen as well with triple bonds. And so we can see that here, okay? So those are kind of some three features that we see commonly from 13.4 in synthesis. And then the next reactions that we saw were two reactions that add water across a carbon-carbon double bond or a carbon-carbon triple bond. It was the oxymercuration reduction in 13.5 and then the hydroboration oxidation that we just finished talking about, okay? And you can see examples of these here used in synthesis. Now, the oxymercuration reduction results in a Markovnikov's addition, right? So let's pretend like I spelled that right. Like I added something there that looks kind of funny, but let's pretend like I spelled that right. Okay, of water, okay, and we can convert an alkene into an alcohol, okay, or an alkyne into a ketone. And these avoid carbocation rearrangements, okay? Now, hydroboration oxidation reactions, okay, result in the syn addition of water, and that's an anti-Markovnikov regiochemistry, okay? And again, we're converting an alkene into an alcohol or a terminal alkyne into an aldehyde. But we end up with, so one of this gives us a Markovnikov's addition, and then one gives us an anti-Markovnikov's addition. And so depending on how you need that addition to happen, you would choose these different pathways, okay, to add the functional group of either an alcohol or a ketone or an aldehyde. Now, the reactions that have been presented in chapter 12 and 13 are related by their mechanisms, okay? Each has a key step that's driven by the formation of a bond between a carbon atom from a carbon-carbon double bond or a carbon-carbon triple bond. And those things are electron rich with an electrophile, which is electron poor. Now here we're going to introduce catalytic hydrogenation, where we have hydrogen gas that adds to a carbon-carbon double or triple bond catalyzed on a metal surface. So H2 is not electrophilic. So the mechanism is really going to differ from the mechanisms we've seen at this point. And so when Carty kind of tries to group where this mechanism goes, it is really hard to group it because we're somewhat uncertain of the mechanism because it happens on a solid catalyst, okay? And so the solid catalysts that we see commonly used are palladium, platinum, or nickel, okay? And these, by the way, are all elements on the common of the periodic table. H2 gas basically readily adds across the double bond. And so it's hard to figure out where to put this in an organic book, and you're going to see it in all sorts of different places because we're not super for sure about the mechanism yet. And there's some hypotheses. I'm going to show you one on the next page, but we're really not sure. And so the big take home here, though, is that we can convert a double bond into a single bond. Now, I want to emphasize something. Most often, this needs to be your last step in a multi-step synthesis. Because, look, we have a functional group here. We can do a lot of chemistry with that functional group. Once we get here, there is no more functional group left for us to do chemistry with. So if you ever make this your first step, then you lose some of that reactivity. So it's just kind of something to think about if you're going to use this in a multi-step synthesis. Is generally it's the last thing you do. Okay. Now, the metal catalyst in this reaction is called a heterogeneous catalyst. So this is an example of a heterogeneous catalyst, okay? Because it exists in a different phase from the rest of the reaction mixture, the catalyst here is an insoluble solid, and it's suspended either by stirring or shaking in a solution that contains both hydrogen and the organic substance to be hydrogenated. Honestly, when I've done this reaction before, I did it with palladium, and the palladium was so fine, and we let it go overnight. The palladium was so fine that it stayed suspended the whole time. So we shook it and then left it in a hood, and this reaction happened overnight. So this is sort of what we think is going on here in the mechanism. Initially, right, the hydrogen and the alkene absorb onto the surface of the catalyst. Okay, and so we see that here and here. As that occurs, people believe that the hydrogen single bonds are effectively broken, producing hydrogen atoms that then kind of hang out here on the surface of this metal. And so the absorption of the alkene breaks the pi bond of the carbon-carbon double bond, and then eventually an absorbed hydrogen atom encounters this absorbed alkene, and the first two carbon-hydrogen bonds are formed, and then after that a second carbon-hydrogen is formed. Notice there are no arrows, we're not pushing any electrons. People aren't really super sure here of this particular reaction. But again, it takes about 18 hours to do this reaction, so this is a relatively slow process. All right. Now, the carbon-carbon triple bond of an alkyne can undergo catalytic hydrogenation as well, right? Because it's got those carbon-carbon pi bonds. That's part of the reactivity. Similar to the alkenes, that addition of the hydrogen removes the pi bond, and it causes the total number of bonds between the alkyne carbons to decrease by 1. So we end up here with a double bond. Okay, so we have an alkyne, it's converted to an alkene, and that's shown in brackets here. Now, because this is in excess, right, you can go directly to an alkane. In general, when people do this reaction, like this with H2 and some sort of nickel and a solvent, it's to go to the alkane, and you use excess. Because if you use an equal, what we call an equimolar amount, then, which is, when we think about stoichiometry, it's a 1-to-1 molar ratio, so 1 H2 per every 1 alkyne. What happens here is that we get a mix of products. And again, we don't really want mixtures of products, because mixtures of products means that we have to do extra separation, and it's just not quite as efficient. Now, if an alkene is the desired product, so let's say you've got a triple bond and you don't want to go all the way to a single bond. If it's a desired product, the catalytic hydrogenation can be stopped at the alkene stage by using a stoichiometric amount of H2 and something called a poisoned catalyst. Okay? Now, a poisoned catalyst is just a metal catalyst that's been specially treated to decrease its catalytic ability. Okay? And that makes it slower and a more controlled reaction. And so a really good example of this is the Lindlar catalyst, and that's shown here. And so this is the Lindlar catalyst. Now the Lindlar catalyst is palladium, right? That's deposited on calcium carbonate and then treated with a small bit of quinoline and a lead salt, okay? And that's Pb. When you see this in reactions, most of the time people just say it's a Lindlar catalyst. Right, like here in 1351, it's a Lindlar catalyst, okay? What you see here as well is sometimes like a palladium, barium sulfate, quinoline, right? And this functions in much the same way as the Lindlar catalyst. It's got that palladium and barium sulfate. I want you to know that the barium sulfate can be used instead of the calcium carbonate. So sometimes you'll see calcium carbonate there. I don't care which one you put on your paper for a test, but you need to be able to recognize that both of these are Lindlar catalysts. I also want you to notice that they give you a cis product. So those hydrogens add in a syn fashion. And so we only are getting the cis isomer here. Now, this book doesn't go over it, but if you wanted to go and get the trans isomer, this book doesn't go over it, but you would use sodium metal in liquid ammonia, and that will give you the trans isomer as well. Other organic books that I've had have talked about this reaction. I don't know why Cardi doesn't here, but if we can get the cis, we can always also get the trans, and so that's something that can happen there. So let's do so we've learned all these new reactions. I want us to do an example here. So, outline a synthesis of Z1-phenyl-hept-2-ene from bromomethylbenzene and any hydrocarbon. Okay, so we've got to go from this to that. So here are some questions that we need to ask ourselves. Does this synthesis require a carbon-carbon bond forming reaction? So if I look, all right, if I broke up there, I apologize. I had to pause it and then restart it. So as I was mentioning before, when we start a synthesis, we want to count the number of carbons that we have. When we count here, we have 7 carbons. So there are 7 carbons here. And then we come over here and count the carbons in our product. So there's 6 here, 7, 8, 9, 10, 11, 12, 13. And we have 13 carbons there. And so when we need to ask ourselves, does this synthesis require a carbon-carbon bond forming reaction? Well, yes. And the way we know that is because we're going from 7 carbons to 13 carbons. If so, have you learned the carbon-carbon bond forming reaction that leaves a carbon-carbon bond in the product? And unfortunately, we haven't learned a reaction like that. So yes and no. Okay, so now we have to kind of put on our thinking caps and think, what could we start with that we know that would leave us with a double-double bond? So we notice that this is a cis carbon-carbon bond, so that's important information. And so can the cis carbon-carbon bond be produced from another functional group? And the answer to that is yes, right? So we can use an alkyne and a poison catalyst and go from a triple bond to a cis double bond, right? And so when we look at this and we think about this reaction, right? That's what we're trying to get. And so the question is, right, where would be the best place to kind of undo this, okay? And the best place to undo this is going to be right about there, where that triple bond is an alkyne, okay? So when we think about this, okay, the very first thing we would see, okay, oh, I have messed up with my structure. Hold on. Got real excited there and I should not have. Goes up and over, and there's our double bond, and down like that, okay? And so we need to undo, I just forgot to write, we talked about it, but I forgot to write it, that catalytic hydrogenation. Okay, and the way that when we do that, then we start with a triple bond. Okay, and then it makes sense with this to undo it right here because we can do a lot with terminal alkynes. They can participate in SN2 reactions. And so we can undo an SN2 reaction, okay? And so when we do that, remember we're left with that triple bond. And then we could also start with our starting material, okay? Now this came from, if you need to go back and review that came from chapter 11. That's what we did right at the end of Gen Chem 1. So, Gen Chem 1, right at the end of Organic 1. So you might need to go back and review that reaction, but we're undoing an SN2 with the terminal there. So now that we've kind of done this step-by-step analysis, we've gotten to our products, now we need to go through and fill in our reagents, okay? And so I'm going to say, okay, look, I'm going to start with this alkyne, right? And I remember when we did an SN2 reaction with a triple bond, we had to do NaNH2 to remove that terminal hydrogen to make it a carbanion. Then we are going to add our alkyl halide. And so that's going to attach. Right there. And then we're going to add H2 and that Lindlar catalyst, or you'll see it written out like this. Right, or the structure of quinoline. They can do it a lot of different ways. There's a lot of synonyms for that. And then we get that cis double bond just like that. So this for us concludes chapter 13.